before the midterm exam. And today we're gonna close the deal about model reduction. I know that the story about the model reduction and description of flexibility is a little bit lengthy, but my objective today is to try to kind of summarize everything in a package that is easily understandable. And then there will be another summary package later today. I hope after, say, 45 minutes, after half an hour perhaps, 45 minutes at latest. Then that's another summary package is about how is that you can prepare yourself to written exam. And then we are having a voting action. And in that voting action, you guys can select the question that will be, for sure, will be an exam paper. And also you will have an opportunity to vote out one question that will not be in exam question. And excuse me, in exam paper. So there will be a total of 28 questions, and actually two of them you can affect by your voting action. How many questions will be in exam paper? That will be a total of six questions. So one will be for sure in a paper, rest you don't know it. So it will come after my meeting with the Surats. Okay. Now, like mentioned, so today what will happen is this. Oh, pen battery is low. Hopefully it's enough that it can carry this today's meeting. And I can see that the camera again, come on camera, please cooperate with me today. I need to wake up my camera one more time. So please stay awake. And now it look good. Maybe maybe I'm thinking that maybe it's somehow related to this cable connection to camera device itself, because as soon as I touch it, it goes off. So it almost looked like there is a cable loose from my camera. Anyways, I'm sure you guys are not interested about my camera settings, but instead you definitely would like to know what are the things you need to master before you stepping into midterm exam. Look at this again. So it's a camera. All right. So before closing the case of model reduction, let's look at the story again. And this is somewhat important because you need to understand the big picture. And when I'm thinking about how is that you can prepare yourself to written exam, of course, what is the most important is the big picture. The big picture really is the one that makes a difference. That makes a big difference. Now, remember where we started the whole story. The whole story started from the need to describe the deformation of a multi-body body. I mean, body in a multi-body system, to be more clear. And we decided that this time we wanted to describe the deformation in a very elegant way by modifying the kinematics. And remember that in multi-body system dynamics, the first thing we do is that we're describing where the body reference coordinate system is located with respect to global coordinate system. All right, so that's going to be described by vector R. The next thing to do is that we will take the orientation of body reference coordinate system into account. That will be carried out by 3x3 rotation matrix. Details how you can describe this, well, there's many different varieties, many different options, including the ones we learn in this course that are Euler angles, Euler parameters, Ortiquez equation, and then there's many others in addition to that. All right. So then what we are describing with respect to body reference coordinate system is the particle location. So particle location, let's denote that as a u bar 0. That's going to be the particle location on its undeformed configuration. So the configuration that there is no mechanical deformation whatsoever. And this is where we stopped in the case of rigid multibody dynamics. I see that my hands are a little bit hanging too low, so I need to raise them up a little bit. So this is where we stop in the case of rigid multibody dynamics. But in this course, we don't stop there. So we do adding the one more component here. And the one more component that we're adding here is a description of deformation with the U bar F. And we concluded that the easiest, definitely the easiest way to describe the U bar F is to use a finite element procedure. And in a finite element procedure, you're discretizing your structure by using something that look like a fishing net. And the fishing net, what that stands for, it stands for elements. And elements, I mean, single element is not yet acceptable solution, but once you keep on adding the number of elements in the finite element method, you are getting the better and better solution. So you're increasing the number of unknowns, and you get a better and better solution. This is what is called convergency. More element, more accurate solution. Now, this is exactly what we wanted to use here. So we wanted to use this finite element equation of motion to solve this guy, vector u bar f, vector u bar f. Now, what we could do to make that happen is that we could just use a brutal force. Like, if you have a lot of force, like, look at this, like this, and not heavy thinker, you can just take a lot of CPU power and solve the equation, this equation as it is. So that means that you will put the acceleration in the left-hand side of the equation, all others in the right-hand side of the equation, and that's it. You just make it happen. And that's possible. Problem here is that if you look at the dimensions of this problem you're solving to describe flexibility that is superimposed to this reference motion or rigid body motion, you end up to have really high number of unknowns to describe the deformation. Because in your typical finite element model, let me see what happened to my camera. So it's looked that my hand is frozen. The light is no longer on in my camera, so I need to wake it up one more time. Okay, camera is back. Now, the problem we're facing here is that number of unknowns is typically very high. And that becomes to be high because remember in a finite element modeling, so if we have this kind of potato-shaped body, we are discretizing this potato-shaped body by elements, which look like a fishing net. And the elements are connected to neighboring elements by nodal displacement, nodal locations. And these nodal locations have a certain number of degrees of freedom. How many? Well, that actually depends what kind of element you're using. But let's say that if we're using a plate element that is shown in the figure here, usually the plate element consists of 6 degrees of freedom. Each node has a 6 degrees of freedom. So 6 degrees of freedom here, 6 degrees of freedom here. So when and so forth, my goddamn camera, please stop messing with me now. Another wake up. I think that it is somehow cable related problem. Okay, so here is 6 degrees of freedom, 6 degrees of freedom, and each one of these nodes, each one of the corners where the elements are connected, there's a 6 degrees of freedom. So even in this simple coarse mesh, you end up to have a very high number of degrees of freedom. And that all needs to be solved when using this technique. And now there is a question. I need to take a look at the question, the comment. Okay, why 6 degrees of freedom? Well, the 6 degrees of freedom depends on the element type. But typically when you're looking at the plate element as a single element, is something that there is a nodal displacement with respect to element reference coordinate system. So it's a vector displacement vector r. So that is in a spatial case having the components along the x, y, and z. And typically there's a rotations around these axes as well. So that's going to be, I don't know how you want to say it, maybe this is an unclear way to say it, but 3 rotational parameters. So that's going to be a total of 6 parameters. But it could be even more than the 6 parameters. Like if I have an opportunity to, later next period to explain some new technology, finite element related technologies, and those methods are no longer limited to 6 degrees of freedom, but it could be more than that. Oh, my head. Sorry about that. Me and my big head. Okay, so now oh my God, and I see that this is completely twisted. Completely twisted, so let me move this a little bit. Oh no, better idea would be to write this plate element here. Here's a plate element, here's a reference coordinate system. So one node here consists of 6 degrees of freedom that are 3 displacement, 3 translations, if you may, 3 rotations. This is a very typical scenario. Then the solid element, which is like a cubicles, like looking like this. They typically have 3 degrees of freedom per nodal location. And these are just the displacement, nothing else. So this would be the element with 8 nodes, and each one of the nodes would have 3 degrees of freedom. But again, it really depends on what kind of element you decided to use. All right, so I was explaining this, that this system solving the equation of motion as it is, that's not going to fly. So it's not going to be a successful way to do it. And that's simply because we have too many unknowns to solve. And you need to keep in mind that you have to solve these unknowns in every single time step, because it goes here. So you need to solve the deformation. You need to know the deformation in every given time. So that makes it like overly heavy to use it in a practical application. So we need to do something. We need to do something for this guy. And this is what I'm definitely going to ask in midterm exam. Okay. All right, so I can see that I'm forced to make some adjustment regarding to how is my screen. So for some reason the screen is moved a bit. So now it looks better. Okay, so this is where I explained in my previous slide. So instead of simply solving this acceleration here, I'm going to use a trick here. And in my trick, I'm going to move from nodal degrees of freedom to modal degrees of freedom. And this is conceptually almost like a mind-blowing thing to think about it. But basically what it means is that we are looking at the way that the structure can deform. Because remember what these degrees of freedom that are associated with this vector u, what is that they're standing for? Well, all they're standing for degrees of freedom. Another way to express that is to say this is one way that the structure can deform. One way that their flexibility can take a place. All right, now if there's a vector u here that consists initially, say, 100,000 components, so there is a u1, u2, all the way to u 100,000. That means that the structure, your finite element model, sorry to say the structure before, but I want to correct that to be a finite element model. Your finite element model can deform in 100,000 different ways. 100,000 different ways. Okay? What are these ways? And are they all important? This is a key question. This is extremely important to understand. Well, first of all, what are these ways? How is that I can know what are the possible deformation modes? The way to solve it is using an eigenvalue analysis. And in eigenvalue analysis, what is that we doing? I'm going to take these drawings off. Here. What is it we're doing in eigenvalue analysis? Is that we're going to look at the structural properties only. Because the way the structure can deform is structural or model ability to describe the deformation. So it's not related to forces. So I'm going to take this mass multiplied by acceleration, stiffness multiplied by displacement. So this is inertia forces, elastic forces, and I'm going to compute eigenvalues and corresponding eigenvectors using an eigenvalue analysis. That's going to give me the ways that these 100,000 degrees of freedom can move with respect to each other. So if there's, to make this more clear, let's say that we have a system with 3 degrees of freedom, U1, U2, U3. This system can have 3 different ways that these U's can move with respect to each other. That many ways that they can move with respect to each other. So if I'm thinking about, maybe I can use it in a way that I describe that as a spring mass system. So these are the nodal locations, these guys. The way this can move with respect to each other is that, of course, there is this possibility of rigid body motion, meaning that they all move left and or right without no spring deformation. Then one possible way that they can move with respect to each other is that the structure getting smaller. It's distracting, it's getting smaller like this. That's the one way that it can move. One additional way that it can move is like these two guys is getting closer to each other, these two guys getting far from each other. So these are the deformation modes. These are the way the structure can deform. How much they deform in this particular way, this will be our unknown in future efforts. So we are not looking at the single degrees of freedom, but more how is a type of the structure can deform and how much it can deform. That will be something that we will keep as an unknown. All right. So here's our matrix that is constructed from these different ways that the structure can move. I know that this sounds like very theoretical. It's hard to get a grip like what is going on here, but I have some other explanation in a minute. Now, with help of this matrix that contains the ways that the structure can deform, I can find a relation between nodal coordinates and modal coordinates. And again, the modal coordinates are the way the structure can deform, nothing else. And now I see that I missed a comment. I see. It's the comment that was something was related to my head. Okay, so now what happens when I do this, when I'm moving from nodal coordinates to modal coordinates, is that I can rewrite my equation of motion as it is shown here. And now this becomes to be handy because what I could do when I'm moving from nodal coordinates to modal coordinates is that I can actually ignore certain deformation modes. Deformation modes that I feel that are not significant, that are playing a minor role in terms of machine performance. So which one I can ignore and which one I can leave, that's going to be the hard decision to make. But we will get back to that maybe today, or if not today, then right after spring break. So anyway, so we can reduce the number of unknowns. And while we're reducing the number of unknowns, we can get another very handy mathematical feature. And another handy mathematical feature is that if these modes are orthogonal, which they will be if I'm going to use an eigenvalue analysis, then there's no relation between modal degrees of freedom. So they are all independent. And because they're all independent, I can solve one modal degrees of freedom and knowing nothing about others. That's you cannot do in a finite time modeling, because in finite time modeling you have the block diagonal representation of stiffness and inertia. But when moving to modal degrees of freedom, you do have that freedom. So you will have a diagonal representation of mass and stiffness. So that's how it goes. All right, I know that is extremely lengthy summary, but still I really wanted to spend some time to explain this to you. Details of eigenvalue analysis. Well, this is pretty much what I explained already. So really the most significant thing to do in eigenvalue analysis is that you're setting forces to be zero. Why? Because eigenvalues and eigenvectors are related to structural properties, not forces. They are telling you How is the natural frequency of the structure? How is the corresponding deformation modes? Those ones has nothing to do with the forces. And this is, of course, when we are speaking about the linear dynamics. In nonlinear cases, they may have some relations, but we are not going to touch that. So we're going to leave that off the picture. Okay? So you're setting forces to be equal to 0. This is already telling you that whatever you get as a result of this will not be absolute responses, but instead they will be something that is telling you the feature of your model, properties of your model. Okay? I know that the solution of this equation can be written like this. This is pure mathematics, so don't put much of an effort to that. And when I'm substituting that information here, this equation, I could get the solution like this. Now the solution consists of two parts. One that is associated to eigenvalue, omega power 2, and the corresponding eigenvectors. Each one of the eigenvalues has a one eigenvector. What that means? It means that if you have a structure like this, which is a mass and a spring, this structure will have a certain natural frequency. All right? And this natural frequency is associated to motion when the mass is moving up and down. So if you have two masses, this will have two deformation modes. Remember this idea about finite element modeling, the same thing here. All right, so I was about to explain, what was that I was up? Oh yeah, well, if you just have one mass here, you know that you can calculate this omega such the way that is square root. This, I'm sure this is omega square root stiffness multiplied by mass. So it goes higher. Oh my God, I got confused. It's this other way around. So is it mass multiplied by, so if there's a high mass, low stiffness, then the natural frequency will be low. So if there's a high stiffness, low mass, the number will be high. I think that this is correct. Okay, so then this is how you can compute it. And the corresponding deformation is that the mass will go up and down. Okay, now once you have this eigenvalue, then how the n-dimensional system will deform, you can get that information by substituting the value here, here, and solving this vector here. That's what we learned last time. And finally, the results, the interpretation of result is that it's telling you the natural frequencies of the structure. And again, if you have a system with 1 to 100,000. So 100,000, not a degrees of freedom, means that there's 100,000 eigenvalues, 100,000 different ways that the structure can deform. Well, if I think about the frequency-wise, how these frequencies will probably look like, well, they probably will be something that if I make here a drawing where this is a frequency, I'm going to have quite a bit of frequency here in low frequency, but these frequencies go all the way to extremely high frequencies. And I know that my head is blocking the view. So if we think about these high frequencies, maybe they are not so important in terms of multi-body system dynamics, particularly because we're going to look at the deformation modes that are very, very complicated and probably contributing very little to overall performance. So we can ignore some of them. And there are even automated procedures to ignore them. And this is exactly what we do in the model reduction technique. Okay. Now, finally, done with the summary. Sorry that it was this lengthy, but I was kind of sensing that we need to look at this one more time, and now we're done with this. Do you have any comments, anything you want to ask this time, or you want to say it on team session? Okay, so a few additional things. Remember the last week we practiced the computed the eigenvalues and eigenvectors of mass spring system that was described by using finite element modeling. And in this mass spring system, that consists of 4 nodal location and 3 elements. And what was that we got as an example and as a result was the deformation modes, meaning the way the structure can deform. All right. This came out from the eigenvalue analysis. And something that you can do with this solution, I mean, the way the structure can deform, is that you can multiply that solution by any number you want. And that is having the certain purpose. And the purpose that, or the reason that you would like to multiply the number by any scalar would be that you would like to scaling. You would like to put numbers to be as close as 1 as possible. Because the computers, they love number 1 and they hate very big numbers and very small numbers. So you want to scale them to be something that is as enjoyable as possible for computers. And now there's a comment which I'm going to take a look. So will I add this presentation in a Moodle? Of course I will. And of course you guys, please, I'm sure you know this, but all my lectures are available in my YouTube channel. So this is recorded and it's going to be available in the YouTube channel. So you can go back and forth in this recording as many times you want. And it's my recommendation to put the subtitles in, closed capturing in, because it helps to understand my talk. It's not going to make the subject matter to be any more pleasant, but I think it's something that is usable for you. All right, so I was here in the scaling. So you can scale these numbers to make them to be as close as 1 as possible. And now what I'm doing here, and this scaling has a certain name, and it is called normalization. And I can do mass normalization, I can do stiffness normalization. It means that eventually I essentially take my mass matrix and I multiply the mass matrix by my deformation mode, like it is shown here, with transpose and without transpose. And then I'm multiplying all that by scaling number. And the scaling number, why I would like to do that, again, I would like to use the scaling number to make sure that the final product here is as close as possible to 1. So why not just put it in a 1? Sure, we can put it in a 1, and now that I made it, and now the scaling number that comes out from this equation will be the alpha, which is square root 1 divided by 5. All right, just an example that you can do this kind of scaling. There is a possibility that I can ask, what is a mass normalization? Mass normalization means that you take a deformation mode without knowing anything about the frequencies. And you're scaling the deformation mode with help of mass, and then it's going to call mass normalization, or with help of stiffness, then it's going to be called as a stiffness normalization, such that this equation will give you 1. Now you need to do the scaling for all modes to ensure that all modes are scaled to be, mass normalized. So why multiply 2 times? All right, so the answering that is that because here is my, kind of what I would like to do is that I would like to multiply my deformation mode, one single deformation mode. Remember that this is the mathematical representation how the structure can deform. This time when I'm looking at the one particular mode is -2, -1, 1, 2. So it's meaning this kind of deformation mode. Now, this deformation mode I'm going to multiply by my scaling factor. All right. This is my operation. Now, if I would like to scale this with respect to mass, I'm going to take this vector account in this side of the equation too. So that's why I need alpha here, I need alpha here as well. So because the unit or the kind of the quantity that I'm looking at is this guy. Sorry, that is a little bit of messy writing, but hopefully that's clear. Okay, now here are the scaling for other modes. I'm gonna just, what I'm doing here is that as a result of my eigenvalue analysis, I'm gonna write my original equation of motion by using a model reduction. And when using the model reduction, I'm originally going to have here 4 components, which are U1, U2, U3, U4, and the corresponding mass and stiffness. And now when I'm using model reduction, I'm first computing the eigenvalues and eigenvectors, and I'm selecting 2 eigenvectors. Why 2? That's a good question. But I'm just doing this in a demonstration purposes. Later, we need to discuss a more thorough manner, like how is it you can select modes and how many modes you should select. But already this time it's good you to know that this is not particular exact science. Of course, what we can do is that we can compute deformation using all the modes. That's going to be the accurate solution, and then start reducing the modes and seeing or monitoring when is that the solution is no longer acceptable. But that's only in a theory, because these eigenvalue analyses are not suitable to compute 100,000 different modes. They don't really work well for that purpose. But anyways, I'm just to give you a demonstration, I'm using 2 deformation modes, the ID number 2 and ID number 4. Why not ID number 1? ID number 1 I want to skip here because it was representing the rigid body motion, and I don't want to deal that here because that will be accounted by using body reference coordinate system. And why not number 3? Yeah, that's a good question, but I just decided to skip it because I want to reduce my model. All right, here finally my scaled deformation look like this. So this came from the previous slide. This came from this slide. So these are my ways structure can deform. I know that is a confusing. So like how the numbers can tell you the way. Well, they can. They can. They're telling like how these nodal nodes are moving relatively with respect to each other. How much? That I don't know. That's going to be my unknown. So now when I'm selecting 2 modes, it means that I will have 2 modal coordinates. Better to put it this way. 2 modes, 2 modal degrees of freedom. All right. So once I have scaled everything, how is my new mass that is now related to modal coordinates, no longer nodal coordinates? I hope that you can recognize my nodal model. Hopefully it's clear. So this is how my modal inertia look like. This is how my modal elastic or stiffness matrix look like. Now they are diagonal representation. And because they are diagonal representation, finally, my equation of motion look like this. And look at this. This is super pleasant. So this is going to be my modal inertia, modal elastic forces, and my externally applied forces, which 2 are multiplied by modal matrix. Why? Because initially, these are expressed in terms of nodal coordinates. I don't have it anymore in the left-hand side of the equation, so I have to convert forces to be expressed in modal coordinates. So how can I make it happen? Again, I'm going to take my ways of deformation and use them to using them to multiply that by forces. Now I'm going to get as the results of 2 components because of 2 modal coordinates, and my final reduced equation of motion look like this. So it's reduced. Not just reduced, but having another important mathematical feature, which is orthogonality. And that orthogonality means that I can write the modal coordinate number 2 and solve that by using nothing whatsoever about the first nodal coordinate, another way around. And that can speed up the computation quite a bit because they have no dependency in each other. So that's how it goes. Okay, so let me see what time it is. So it's 5 minutes to 1. All right. Now you may wonder, there's something interesting which I really wanted to explain to you. Okay, so now once you get the solution, once you're solving P's, from this equation, these model coordinates, once you solve them from this equation, what you can do with the p's? Easiest way to visualize and interpret the p's would be to put them back to the nodal degrees of freedom, because nodal degrees of freedom clearly has a simple physical interpretation. How you can do that? Well, use this relation again. You have this relation, which is a u multiplied by, I have no idea what this is called, psi, phi, never mind. This is the way the structure can deform. This is my p's. These are the ones you're solving, and as a post-processing procedure, you can go back to the nodal degrees of freedom. You can see how the structure deforms. Is this important? Well, it is, because remember finally going back to multi-body system dynamics. Remember what is that we're solving is this guy here. We need this guy. So we need this nodal degrees of freedom. Whole story was like this. Okay. Finally, I'm done with this. Now let's look at an example. Let's look a little bit about the real life case. So I have here a crankshaft mechanism. And the crankshaft mechanism is modeled such the way that the crank here is assumed to be rigid. So it cannot deform no matter what. Piston here is considered to be rigid as well, but the connection rod is modeled as a flexible body. Okay, so let's look at the connection rod. And let's look how the connection rod is. I need to take these drawings off because it's no longer clear. How this connection rod is connected to neighboring bodies. Well, as you can see that it's connected to neighboring bodies via a revolute joint. Then the obvious question is that now if you wanted to model this connection rod by using finite element model, what kind of boundary condition you should introduce to your finite element model? And the boundary condition is that should you attach to your finite element model to ground when you're conducting the naked value analysis? And if you decided to do so, how you should do that? And options are that, first of all, you don't attach your finite element model to ground, but you leave it as a floating body, the body that can go left and right, up and down in a space. It can rotate, so it can have this rigid body mode. That option number one. Option number B is that you are introducing simply supported beam boundary condition. Simply supported beam boundary condition is that there is a displacement restricted in this end, and the displacement in y direction is constrained. Motion in x direction is allowed. Or finally, you just introduce the fixed boundary condition, meaning that you attached to the structure to ground by fixed joint. Which one you should use? And let's set the competition in this regard. So the competition is as follows. Okay, how to set the boundary condition? Again, it's like I can see my slides are a bit twisted to the right-hand side of the equation, right-hand side. Okay, anyways, what method you should use? Method A, B, C, or something else. So let's put the competition on. So let me see. Here's my Socrative, and I'm gonna launch this Socrative. Oh yeah, okay, so it's on. So what do you feel that is a correct way to do this? Correct representation of boundary condition. Boundary condition. Okay, then there is a question, how we can find the useful degrees of freedom? Because still we have a lot of eigenvalues and do not work with a model with a lot of nodes. Is there a method? There is a method. There is a web method that we can automatically select the most significant ones. But also you can use your common engineering sense. Common engineering sense would be that you are visualizing the deformation mode and you're thinking whether or not you first of all can have a loading such that the deformation mode is significant. And second of all, if it really is introducing the deformation way that you feel that is significant. But it's unclear statement. So how you can do that in all cases, that's going to be a little hard. But anyway, so Socrates is on. So we got the first question, first answers, or first uh, success rate guesses. Mine is this. Why? Because can-do attitude. 100%. So I'm thinking that's going to be 100% because it's so obvious. It's so obvious. Putting a little bit of pressure to you. Okay. And then I see that soon I need to move on to summary section. It's 1 o'clock. So there's somebody that is close to me. So there's 98, but not. Oh, there's 100%. Good. Another 100%. Another 100%. I got 23 answers. I have 28 views in my YouTube channel. So pretty much, I just need to find it out my real pen here. Okay, so now I see that some of you are really clever. So it's saying the 80% plus minus one. Okay, yeah, 500%. That's my guy. That's my can-do attitude, man. Very nice. Okay, so let me see. 23 answers. I am gonna put it on already. So this is how it looked. I think that I don't have any more answers to come. So I'm gonna wait a couple more seconds and then we'll see. Then we will see. Oh, this is not getting any bigger or smaller, so it's always having the same dimensions. Okay. Oh, 27. So I got quite many additional answers. So now I'm feeling that this is pretty much done. So let's take a look. Oh my God, it's not exactly the 100%, but it's close to that. There is a joke involved with this. And the joke is that you can select any ways you want, and it's still going to be correct, any ways you want. So the correct answer today, the success rate wise is a 94. 94. Okay, how come? Here comes something important because remember, let me see. Oh, this is the way to get rid of that. Okay, remember that this method that we are looking at here, it's called floating frame of reference floating frame of reference formulation. This is the correct name, floating frame of reference formulation. Where this name floating frame is coming from. That's something that I would like to explain to you next. Okay, to understand that, so we need to actually look at the deformation of this connection rod. So let's look at the deformation of the connection rod. That's the way that we're gonna, I'm sorry, that is a little bit unclear writing here. So I'm gonna put them, I'm gonna model a cantilever beam by using these deformation modes. Method A, B, and C. Now let's see what happens here. In the first set of modes, my reference coordinate system, which is a coordinate system that I'm using in my finite element modeling. It is left to be such that it's not attached to any of the material point of the structure or of the model to be more specific. So it means that, I have here no boundary conditions. I'm just setting, the structure. I'm kind of putting that structure to float in a space, and then I'm going to compute my deformation modes based on this floating assumption. Okay, so if I originally have a beam like this, and here is my coordinate system that I'm using in my finite element modeling, there's no boundary condition. All right, so the first there will be rigid body modes, so the structure will move left and it go up and down, so those will be rigid body modes. It can have a rotation as well. But the first deformation mode will look something that it's going to change the color here. The color will be black here. So first deformation mode will be something like this. This is like a banana mode. What happens in this banana mode is that if you look at this point here, that was originally in the origin of the reference coordinate system, is no longer in the reference coordinate system, but it is attached to that particular point. And it is traveling, obviously, to y direction. How much? Well, that of course depends how much is this deformation is affected, but it is no longer attached to that point. What about the second deformation mode? It will look like this. Oh, sorry, that not the perfect drawing in another end, but it looked like this. Here again, point is detached from the origin of the reference coordinate system. What it means if we go back to this cantilever beam. So in the cantilever beam, gotta make like really extreme deformation. Let's look at this like this. Okay, and let's change the color one more time to make this clear. So let's put it green here. Look at this deformation mode. This deformation mode. Let's place this green deformation mode to describe this behavior. All right, so it's like that. So where the body reference coordinate system will be in this case? Well, it will be here. So it will be here because look at where it is here. So it's here. So it's no longer attached to point, but will be moving. It will be floating with the body. And this is where the title floating frame of reference formulation is coming from, because you can use modes that is having no boundary condition but are free modes. And in the case of free modes, reference coordinate system is no longer attached to any material point. It is still following the material point, because even if you say, okay, this is no longer, say, cantilever beam, but this is a pendulum. So if you're rotating the pendulum, sure, yeah, what happens is that, this reference coordinate system will follow the large reference motion, large rigid body motion, if you want to say it this way. But whenever you're introducing the deformation, it is detached from the body. So that's where the name floating is coming from, because it's not rigidly attached, or not necessarily rigidly attached, but it is, what is the best way to express it? Following, floating, following body. And that's what happens. All right, so this was my first scenario. Let's see how messy it will be when I'm moving one more color. So what if I'm going to use this boundary condition here? Now I have my reference coordinate system here. And if I want to use this deformation mode to describe this condition, how the reference coordinate would be, it would be like this. But the shape of the deformation, shape, is here the keyword. Shape will be approximately same. And that's why if you select to use a method A or method B, they're producing roughly same results. So does it really matter, like, if the reference coordinate system is moving? No, it doesn't really matter. Because remember what we're doing in multi-body dynamics is that we are describing particle. Let's say the particle that is now located in the free end of the cantilever beam by using this equation. All right, and now let's make it to be thorough. Now, what really matters is that do we have a same final destination? It doesn't really matter if you do this trip by moving this guy or this guy or this guy. But what matters is that do we have a same final destination? And we do. We do, regardless of what reference condition we're using here. So if you have this reference condition, and let's say that your global coordinate system is here, you're first traveling here, then you are counting the orientation and they're going here. So that's exactly the same as going here and here. This point with respect to this coordinate system will remain constant, no changes. Okay, D. I know that this is now almost extremely too messy to follow, but D option here would be, let me change the color one more time, yellow. All right, so here will be the body reference coordinate system and the deformation would be like this. Again, the final destination will be the same, no difference. That's why you can use whatever method you want. Some other way, maybe this is possible too, so I'm gonna give you the points too, even if you voted for option number 3, D, not 3, but D. And with that, I think that I need to, okay, here's the summary. So the floating frame of reference formulation, the name comes from the fact that the modes that I used in modal reduction can be obtained by using free boundary condition. And in a free boundary condition, reference coordinate is not rigidly attached to body, but is floating with the body, floating, following, kind of like coming along, but not completely. I don't know what that is, like what would be a good way to express that in English. But anyway, so hope you got an idea. There is one more thing that I think that I need to skip this. This is one more way that the modes can be selected. I have a feeling that this Craig Bumpton is something that is explained by Jussi Sopanen. Oh, excuse me, Dr. Jussi Sopanen. I'm almost made a mistake here. I'm not going to explain it today because we are simply running out of the time. I got the warning in my OBS. Something about bitrate. Let me see. Is it mic settings? Okay, so mic settings are now changed, but I still got the warning. Another day I was listening to the lecture number 4, and my voice was like a robotic voice. Not very pleasant. Let me try this. No, I still have the warning here. Okay, let me ask. How is that you hear me? Can you hear me okay, or is it like a robotic voice again? Let me see your feedback. Voice is okay. Okay, great. Great. Then something else. Something else is summary. Okay. So let me see. So you don't see this. So I guess that I need to change the view. This one. Okay. Exam. And one more thing, I need to move this a little bit, make this a bit smaller here. Like this. Okay, here are all the questions that I can ask from you. Again, remember we have this deal. So I have to limit myself. I have to control myself. And the way that I need to control myself is that I can only ask questions that are listed here. So I cannot go outside of the questions that are in this presentation that I'm about to share with you. So now, this is already telling you that, okay, well, the only reasonable way to prepare yourself to exam is by studying the questions and ensuring or making sure that you can answer all these questions. That will be a total of 28 questions, okay? To make your life even easier than that, I promise to have this voting action that we will have one question that will be in exam and one question that will not be in exam. Uh, and then the one more thing that I will promise to you is that I will keep your star rated. Star rated means that I'm going to value how important is each one of the questions. And it will be not the questions, but the subject matters. What is the importance of certain subject matter? And that will be rated by stars as is a usual business. Okay, so there's a question. So the first question is that, so does that mean there will be no numerical computation like in the last semester? They What will be there is that these are the questions, and as you see, some of the questions are a little cumbersome to answer by just writing, explaining in a text. An example would be, say, Rodriguez equation. It's quite a bit of effort to explain that in writing. So what will be offered to you is that you will have this opportunity to write your answers in a pen and paper. Take a picture of your answer by using your mobile phone or whatever means that you can convert your answer to be in a PDF format and upload the PDF as an answer of that particular question. So each one of the questions, there is this opportunity to write it down using your keyboard or uploading a PDF. Both will be okay. So whatever you wanted to use. And then there's another question. So what about Craig Bampton? Craig Bampton will not be in a part of the question. I've got there is a question. There is a final question number 28 that is about Craig Bampton, but I will remove it. So it's not going to be part of that. All right. So these are the first set of questions. These are the ones that you saw earlier. So no surprises here. These are follow-up questions. So a total of 11 questions about kinematics, 3D kinematics, which is quite a bit of questions. And now, which ones are the valuable ones? Which are the ones that really make sense you to familiarize yourself to that particular subject matter? Well, here comes ratings. 3D kinematics as an big picture, rated as a 3-star. How is the best way to interpret these stars? Well, my advice to you is that if you are aiming for, let's say, maybe it would be better to say it this way, that if there's a stars, 5 stars, that is something that if you're aiming for a grade that is equal than 1, make sure that each one of the topics that are rated as a 5-star you can master, which are not so many. If you're aiming for final grade of 2, then the topics rated as a 4-star will be enough for you, and so on and so forth. So if it is 3 stars, that's going to be 3. So this, if you're aiming for number 3 or higher, you should look at this topic. Okay, and so this is medium importance. Let's put it this way. Not so difficult, particularly if you have this opportunity to write using pen and paper. And one more thing, because this is a module exam, meaning that this is online exam, and I have no means to monitor you. I cannot really see what's going on in your, I don't know where is that you're doing the exam, in your place, in your cubicle, or whatever is the place that you're actually doing the exam. I cannot put the camera on because I guess that's against the law. So you can use whatever material you want, except your fellow students. But you can have a lecture notes open. You can have a YouTube channel open. You can watch the YouTube channel, and everything is possible. So, and if you feel that you need to get additional materials from, I don't know, from other book or something, go ahead and use it. Go ahead and use it because there will be no way me to monitor if you are using additional material. So let's just make it all free. Okay. So it's like all doping accepted. Not all doping accepted, but all material accepted. Let's put it this way. Okay. So we here, and where's my pen? Okay. We're moving on. Look at this. Rodriguez equation. Rodriguez equation rated within 3D multi-body dynamics as 5 stars. So the questions related to this particular subject matter, make sure you understand them. And again, from what I did not explain in the beginning, that Rodriguez equation, what is a concept of that? It's extremely important to understand that this is all about the original vector, which is having um, a random orientation. What you're going to do is that you will use a unit length vector v, and the unit length vector v will be attached to your original vector, and then you're going to take a hold of the unit vector v. You will introduce the rotation that is amount of theta. All right. Now what you're going to do is that you will take a look at the original vector on its original configuration and its final configuration, and you're deriving relation between these two configurations. Excuse me. This relation will be your rotation matrix. Okay, so then there's a question about when if there's a need to write a matrices, can I use a latex? Sure, you can use latex or Word or pen and paper or whatever you want. Of course, if latex, then it's gonna look great, of course, but this time the visual appearance is less important, so it's not so important than in other cases, because this is just an exam. Okay, then that was about the Rodriguez equation. Euler parameters is related to Rodriguez equation. And what is that you're doing in the case of Euler parameters is that the certain components within this equation will be named, will have a different name tags. And these name tags will be called as Euler parameters. Now make sure that you don't mix Euler angles and Euler parameters, because they are conceptually very different. Very different even in the sense that there are 3 Euler parameters, 3 Euler angles and 4 Euler parameters. So even the number is different. So make sure that you are not consider that they are somehow brothers or related to each other. Of course, there's a relation, but they are not as close as the title implies. Okay, with that, I see that I need to speed up a bit. Mathematical properties of rotation matrix. Not much to study about that. It's just that the rotation matrix is orthogonal, and the transpose of the orthogonal matrix means that the mapping order will be changed. So if it is originally from local coordinate system to global coordinate system, transpose would mean another way around. Order of rotation cannot be changed in three-dimensional space. But something that isn't important is that comparison of different methods. I mean, if you're using 3 parameters, you're always gonna have the problem of singularity of some kind. But usability will be great, because for human brains, the 3 parameters is easy to understand, whereas 4 parameters is beyond the limit, usually. So you can write us something about that. Then robot kinematics, it's rated as a 4 stars, so maybe not necessarily this important, but this is somewhat easy to understand. So make sure you understand the 4x4 transformation representation, that you understand how that can be used in a case of Denavit-Hartenberg rotations, or kinematics. Kinematics would be the better way to say it. This is how it goes. So the Denavit-Hartenberg is based on 4 parameters, and these parameters are explained in these 2 figures. And each parameters can be expressed by using 4x4 transformation matrix. Once you put them in one package, meaning that you are taking Then simultaneously into account by multiplying these matrices, this is how the representation look like. And the idea of the method is to build a table that is telling how these four Dynamite-Hartenberg parameters are. Once you know these parameters, then it's a matter of substitution. What you can get as a result is a robot kinematics, which is great. So it's very simple, straightforward procedure to use. Okay, moving moving ahead. Velocity of particle. This is rated as a 4-star only because if you really understand that, okay, the angular velocity and time derivative of rotational generalized coordinates is not the same, that would be a big deal. That would be a big deal. But if you understand that these two things can be related with help of the G matrix or G matrix, that's a great thing. That's a great thing. So how it goes then in real life. So you can express your equation of motion by using angular accelerations. And from angular accelerations, you can go to angular velocities. But from angular velocities, it's not easy to go to positions. You just, let's say that the positions are orientation, to be more specific. Let's say the orientations is noted as this. This is a vector. This is a vector. And this is a final position. This you cannot jump directly. You just cannot. You have to take a detour. And the detour is G. That's how it works. Acceleration of particle rated as a 2 stars only, so not particularly important. And only one question that there's a lot of slides to explain, like how inertia tensor can be related to acceleration of rotation of generalized generalized rotation coordinates. And it's all about the G. So the answer is G, what makes it happen. Final explanation is extremely lengthy. And maybe I don't want to ask this because it's not so particularly important and extremely messy explanation. So it all needs to you need to go all the way back to the how is a generalized inertial forces. And in generalized inertial forces, you will have this explanation of acceleration. And this is where you have the G. So it's a very lengthy, complicated explanation. Finally, when you do all that, you see that the way you can do this relation is going to be with help of the G. This is going to be your inertia tensor, and you can map that to any rotational parameters you want. And again, how you can make it happen will be with help of G matrix. So lengthy explanation. This is equation of motion, which there is no question. Then some practical questions, number 13 to 15, deformation. And first one was general description about flexible bodies. Why it is important to describe flexibility? Well, they increase the model accuracy. That would be the one answer. And also, if you wanted to obtain strains or stresses, that's another question. Another answer to that question. So linear and nonlinear deformation, make sure you understand that difference. You can always use that in your answers. Lump mass approach, which is not strictly speaking within the family of flexible multi-body dynamics. So you have rigid bodies that are connected together via spring elements. So it's a one application of rigid multi-body dynamics. And then this extremely important thing about floating frame reference formulation as a general idea. And general idea is that this is the guy that you wanted to compute using finite element method. Comparing different methods, lump mass, floating frame reference formulation, that's something that is worth the study. Finite element modeling, make sure you understand the basics. Basics that the finite element model is all about how you're predicting the life between the nodal location to take the place. How is a life between the nodal locations? So it's all about that. Life between the nodal location can be, in easiest case, to be described by using polynomials. Polynomials are a little bit problematic because, if I would solve the polynomial unknown coefficients, they tell me nothing. It's very hard to see what that actually means in real life. So the physical interpretation is not so clear. So what I wanted to do is that I wanted to express these unknowns by using not a decrease of freedom. And that will give me safe function matrix or safe functions, which are telling me that if I'm introducing the one or displacement in the one nodal coordinates, how is that the particles between these nodal locations are following this one displacement. Derivation of stiffness matrix, not important at all. Safe functions. This is what I just explained, 5 stars. So it's important. It's important. So what is the physical interpretation of safe functions? How you can get the safe functions? And again, it's coming from the polynomials. They are telling you that if I'm introducing the unit displacement to 1 degrees of freedom in my element, how is that the particles between the nodes are expected to follow that displacement? Then let me see what else I have here. Solution techniques. As a 2 alternatives. 5 stars here. So I can use direct solution or I can move on to my modal coordinates. This is the cumbersome. This needs some thinking. This needs some serious thoughts. Make sure you understand that because it's extremely important to understand. Oh, look at that. There is a typing mistake. This guy should not have dots. So it should be without dots. Eigenvalue analysis as an analysis. 3 stars. So it's a fairly important. And then modal reduction. Oh, come on. Look at that. I cannot even count that far. So how many stars is that? That's 10 stars, maybe a little less. Okay, this is something that make sure you really, really understand how it goes. It's all about how you're moving from nodal degrees of freedom to modal degrees of freedom. This can be equal. So that's all about that. And then the final one is correct quantum, which I'm not gonna expecting you to master in a written exam. So these are the final questions. Polynomial related Pascal's triangle. Safe functions, what is that safe functions are describing, how to obtain safe functions, physical interpretation of eigenvector, eigenvalue, how to conduct an eigenvalue analysis, how mass normalization of eigenvectors, what the reference condition means in the floating frame reference formulation. Reference condition is exactly how the reference coordinate is expecting to follow the deformation. Remember this connection rod? In a connection rod, we have this option that there is floating, no constraints, simply supported beam, or a fixed beam. So that's what it means. So it's meaning that how the reference coordinate system is following the deformation. That's what the reference condition means. By the way, this example about this connection rod is quite amazing that you can select the reference condition any way you want. It's a little surprising because in the linear dynamics, you know that if you compute eigenvalues associated to free boundary condition, the eigenvalue will be different when comparing the case with simply supported beam, which will be again different when comparing that to fixed boundary condition. But you have to understand that the eigenvalues and eigenvectors are linear dynamics, so they are linearized with respect to reference coordinate. Whereas the multibody system dynamics, we are describing the nonlinear dynamics. So that's why this confusing thing, that doesn't really matter how you do it, how you introduce the reference condition. But what matters only is that how the deformation look like. And if it physically appears to be the same, then they all will produce the same results. Confusing. And then what I need to leave for lectures right after spring break are matters related to how to select the modes. So we did not discuss about this, so forget about this. These are my final questions. Oh, look at this. Where the world floating is coming in a floating frame reference formulation. This is not going to be in a part of the game, so it will be off. Okay, then how to prepare yourself. My advice to you is this. What really matters end of the day is that you must have a can-do attitude. I know that some of the matters we've been discussing is extremely theoretical, extremely painful, to put it straight. But don't get confused. Don't get confused. You do have the power to solve it, and you can answer these in a successful way. For sure you can. For sure you can. Okay. Now I know that I'm about to close. This is my last slide today. Yeah, and I would like to close here today. And it's not yet hour and a half, but it's hour and 20 minutes. So what will happen next is that I'm gonna stop streaming. I'm gonna stop recording, and I will send you an invitation for a Teams session. Oh, one more thing. I almost forgot. This is extremely important. Sorry about this. Okay, let me see how this works. I need to go. Hold on. I need to. Guess that I need to. Okay, just a second. Mm, the final thing we need to do. Final thing we need to agree is this voting. Here. Um. Here. Let me see. I think it is this one. Yep. Okay, now I just need to figure it out how to play this to you. I guess that I need to put this in a browser. Okay. Sorry that I did not make this before the lecture, so I need to log into Moodle. All right. So once you get into Moodle, this is how it looks. And now I guess that you don't see this, so I need to change some capture settings. This one. Okay, this is a questionnaire that is available in why not yet visible. Now it's visible. This is a question you can find, a website that you can find in a Moodle site. Now, so these are the possible questions. I can already check like what is that you're voting. Okay, so choose the question that you would like to see in the exam. Select as many questions you like, and it simply goes such the way that I'm gonna summarize your votes, and then once I have made the summary, I will let you know what is the question that will be in the exam paper. And I'm hoping you to do the voting right now. So please log into to Moodle and do the voting, because I would like to announce the winner, which is the question that will be in the exam paper tomorrow afternoon. So make sure that you are doing this voting action today, and if not able to do it today, make sure that it is ready tomorrow morning. I'm going to close this voting at noon tomorrow, and then I will let you know what is that the correct solution is. And then, all right, and then once you are doing the selection, then you can select the one that you hate the most. So what is the question that you like the most, or questions that you like the most, and what is the question that you hate the most? Okay. Any questions or any comments? We will see in a team session momentarily, and we will can continue to discuss about this in a Teams. Okay, so let's close this. You will get the link for the team session momentarily, so take it easy and make sure you have a can-do attitude. We are not going to see next week Wednesday because it's a spring break. Not for you, of course, but for many others. But we're going to see week after that. I think that's March 3rd, I think. Okay. No, it's not going to be March 3rd, but it's something else. I don't know what day it is, but after 2 weeks anyways. Okay, take it easy. See you soon.